continuous random variable again. So in a linear transformation, remember that shape, center, and spread are the things that we're talking about and what happens. So when you add something, positive, negative, or zero, to each observation, you change the mean, median, quartiles, and percentiles, but do not change the shape or the spread. So like your range is not going to change if you added 10 to every score. Your IQR doesn't change, and neither does your standard deviation. And that's what we already learned that, but it's applying to this continuous random variable as well. Multiplying or dividing by something multiplies or divides the measure of the center and the location by that number that you're multiplying by. They call it b in this case. And the spread changes by the absolute value. So like even if it's a negative number, let's say it was -7, you're changing it by 7 units, but does not change the shape of the distribution. And we'll see some of this in action. They talk about this linear transformation as y equals a plus bx. That's one of the things that you can have on your calculator. Remember, they have ax plus b and a plus bx. And they use it as a plus bx. And x is that event that we talked about yesterday, so like rolling the sum of 5 on a die or something like that. Getting 1 goal in a hockey game, that would be your x. And so when you're looking at the means and the standard deviation, for example, down below here, the mean, as you see it, gets transformed by doing that. And the standard deviation does not have something added to it, but it is multiplied by the number that you're transforming, which is a little bit different than you might think. But that's a measure of spread, not center. Then down below, whether we're dealing with data or random variables, linear transformations are the same. I said that just a little bit ago. They apply to both the discrete and the continuous variables. So for example, in a large stats class, the distribution of x, which are going to be the raw scores on a test, was approximately normal. You're going to see this phrase a ton. So every time that we're trying to do statistics, this red highlighted phrase is something that you want to see, because that's how we do our statistical analysis. It has a mean of 17.2 and a standard deviation of 3.8. And the professor decides to scale it, kind of like what we do in our class, where we've added 60 points to the first exam and 60 to the first and 50 to the second. And they do that by multiplying the scores by 4 and then adding 10. So we wanted to find y, the new variable, after this linear transformation, to be the scaled score. And we're going to find the mean and the standard deviation. So if we define it, we would say that y is going to be equal to a, which is whatever we're adding, plus bx, and the x is the event of the raw scores, and the y would be the new scores. After we do that, we know that the new mu that we're talking about, the mu of the y, that is, the mean does the same kind of thing that the equation would do for us. So we're going to have 10 plus 4 times whatever that old mean was, which was mu x. And our standard deviation of our new variable y does not get the 10 because it's a measure of spread. It just gets the 4. So this would be 4 times the standard deviation of whatever the x variable was. And we can find each of these things using the information up above. So if I look at what the new mu is, instead of 17.8 or 17.2, it would be 10 plus 4 times that 17.2. Whatever that turns out to be. My sources say 78.8. And the new standard deviation then is going to be 4 times whatever our old standard deviation was, 3.8. And my sources say that should be 15.2. So then we can use some statistical analysis on this. So we want to know, in this new system, what's the probability that a randomly selected student has a scaled test score of at least 90? So what we're asking ourselves here is, what is the probability that my new scaled score, so I want the y, not the x, make sure you use the correct lettering, is greater than or equal to 90. And we know that from the past that we do this when we talk about standardized scores, so we standardize this. we find the z-score. So now my z-score is going to be the value of 90 minus my new mean, which was 78.8, divided by my new standard deviation of 15.2. And when I divide, I get 0.74. And so then the actual statement of what I want here could be translated to say that I'm looking for the probability that my z-score is going to be greater than or equal to 0.74. And we can do this on our calculator using the normal CDF, where you do normal CDF 0.74 comma 99, because we're talking about standard deviations. And then when I get that, hopefully you get something like 0.2296. In this second example, El Dorado Community College considers a student to be full-time if they have 12 to 18 units. The number of units X is going to be a randomly selected El Dorado College full-time student taking fall semester, has this distribution. And we want to find the mean and the standard deviation. So this is actually what we did yesterday. So if you want to find the mean of this information, and we'll call it X because they call it X up above, then I take the event of 12 credits and I multiply it by its probability. And I keep going with each different credit load and I multiply it by its probability.
And this is on the AP exam like this, they're
Yes.
not going to give us like 7 or like a small amount, right, of different data points.
Well, anything you see here would be typical of what you might see on the AP exam. And I get 14.65 as my mean credit load. So this means that on average, a student at this community college, based on our sample, is taking about 14.65 credits, or between 14 to 15 credits. If I want to find that standard deviation, remember we can't find standard deviation directly from the data. We have to find the variance first. That's that big annoying thing where you take the score minus the mean and then you multiply by its probability and all that kind of stuff after you've squared it. So in the next group here, this is going to take a little bit of time, so I look for variance first. And so I take the score 12 minus...
What letter is that for variance? Sorry.
So just a reminder that standard deviation, which we call sigma, is equal to the square root of the variance, which we call sigma squared. Okay, and in this problem we're finding the variance first so that we can find our standard deviation. So this process, as I do this, is 12 minus 14.65 squared times its probability of 0.25 plus 13 minus 14.65 squared times its probability of 0.1 dot 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 dot, and I go all the way to the end, and then I'm going to have plus 18 minus 14.65 squared times its probability of 0.15. And when I get done, I get the value of the variance, which is 4.2275. And I figured I'd skip writing all those things down on the AP exam. Make sure you write it out.
Oh.
But here, we're taking our notes, so I'm going to shorthand it because I figure that you can figure out what that means. So then the last step, of course, is to find that standard deviation, which up above we talked about. So if I want the standard deviation of this information, I'm going to take the square root of the variance of this information. Or in other words, I'm taking the square root of 4.2275. And if I take the square root of that information, I get 2.056. So if we talk about this, remember the phrase in context means you have to refer back to the paragraph that they started out with. If I was talking about the mean, I would say that on average, students who are full-time at El Dorado Community College take, on average, 14.65 credits. And if I'm talking about the standard deviation, we would say that on average, the number of credits taken by a student differs by about 2.056 credits off the mean, or off the average number of credits, which is 14.65 credits. In Part B, they define this new variable. There's going to be a tuition charge for randomly selected full-time students at $50 per credit. So now we need to find the mean and the standard deviation. So what this is talking about is that the cost of what these people are going to be paying, actually I'm not going to do this, sorry. This new variable, t, is going to be 50 times whatever the credit load is, $50 per credit. So what does that mean for us? That means that our new mu is going to be equal to 50 times whatever our x value is, or in other words, 50 times whatever our mu of x was, if I'm finding the new mean. So I go back and I look at what my mean was before, which was 14.65, and I just multiply by 50. So I have 50 times 14.65, and that turns out to be 732.50. And if I want to find my new standard deviation, oh, I probably should put down the t's here because we're talking about this new variable. Sorry, I didn't write that down. My new standard deviation will be whatever the standard deviation was times my old one, so or 50, the new cost per whatever, and my old standard deviation was 2.06, so I just multiply the 50 times the 2.056, and that comes out to $102.80. And so it's kind of what you would think it would be with a transformation. If it's 50 bucks per credit, go look at your credits, multiply by 50. If the standard deviation is 2, go multiply by 50, you got 100. Okay, kind of what you would expect. In this next part, they talk about, in addition to these tuition charges, they're going to assess a student fee per semester. And they're going to say that C is going to be this overall cost for the randomly selected full-time student. And now we're going to find the mean and the standard deviation. So my cost, if I do this new thing, is going to be the 50 times whatever my mean was, but I'm also going to add on $100. And if you recall on the previous slide, we talked about one of these things is affected and one of these things is not affected. So if I look at the mu for this, mu of my cost is going to be the 50 times whatever the mu was for my original data, which was the credit cost average plus 100. Or in other words, it's what you think it would be. It would be the 50 times, was it 14.65, right? Plus 100, which turns out to be 832.50, which makes sense because if you look up above, it was 732.50 and you added on $100. Okay, so that makes sense. The weird thing, or maybe weird, is that when you talk about the standard deviation of this thing, remember that the 100, since it's a measure of spread, does not affect the standard deviation. So this thing is going to be just 50 times the standard deviation of that x, or in other words, 50 times the 2.056, so it's still 102.80. So the spread is not affected, just the movement of where that graph is affected, which is kind of, to me, is a little bit strange intuitively. You would think that it would change in distance, but when you really think about it, it makes sense. It's still the same shape. So this last part is always about contextual meaning or definitions or things like that. They always ask a question like this on the exam. Talk about the shape, center, and spread of all three. So